Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. And a pleasant afternoon. At this moment, I am going to discuss about algorithm for minimum spanning tree on data structure in algorithm. So first is, what is minimum spanning tree? Minimum spanning tree is a subset of the edge of a connected underdirected graph that connects all the vertices together without any cycle and with the minimum possible total weight. So this minimum spanning tree is refers to a collection of the vertices, which is the point, and edge, which is the connection between the point. So every vertex in the graph is reachable from every other vertex through a series of edge. So there are no isolation in these connected parts. So the edge, the undirected graph, when we say undirected graph, the edge is the edge do not have a direction. They simply connect two vertices without indicating a specific starting or ending point. So when we say minimum spanning tree, it is a way to connect all the vertices in the graph with a minimum total edge weight. This tree is a type of graph without any cycles, so it is a closed loop. So in the case of MST, so it is a subset of the edge of the original graph that form a tree connecting all vertices without creating any cycles. So the essence of this MST is simplified connected version of the original a connected version of the original graph that retain all the vertices but achieve this with the least possible total edge weight. So to ensuring no cycles are formed. So this so in my presentation I have the prepared example of the main graph and then through this main graph we are going to make a spanning tree through this main graph. So as what you see in this slide that I already made a spanning tree using the main graph. So to make a spanning tree, we need to take all the vertices. So as what you observe, these vertices I'm pertaining to the letters of the main point or the nodes that is appear in the screen, which is the A, C, B, and the D. So as you see that I arranged it already. So this is one of the example of the spanning tree. So according to the definition that uh, the spanning tree is there is no cycle in the graph. So in the example here, this is in the main graph, there is a cycle between A and B, C and D, and C and A. So there is a cycle. So as what you observe in the minimum spanning tree, so there is no cycle. It means there is no repetition of the process. Like A is connected to B and B is connected to C and C is connected to D. And then the other example of the spanning tree is A is connected to B and D connected. Minimum spanning tree has a three uh, has divided into three category, which are the greedy algorithm, the frame algorithm, and the Kruskal algorithm. So first is the greedy algorithm. So greedy algorithm is an algorithmic paradigm that allows the problem-solving approach of making the local optimal choice uh, optimal choice at each stage with a hope of finding a global optimum. So uh, each stage we select a local optimal value with the hope of getting the best possible solution. So it is a useful in programming methodology. So this approach is simple, easy to code and implement, and have a reasonable running complexity. However, the main drawback of for this method is that there are very few cases wherein we end up getting a globally optimal value. So in this example, we will see how the algorithm makes a local optimal choice, however, ending up a non-optimal solution. So in this tree, we are required to get the largest root leaf sum. So, and that is starting from this root node here, we have to find an ending at the leaf node and having a sum of a node as a maximum. So let's start our root node in number 3. So as you can see in number 3, this is our sum. This is how we are going to start our greedy algorithm approach. So in the minimum spanning tree. So here we are going to start choosing number 3 as our root node. So in here we have a two possible path, which are the 4 and the number 7. So however, if we make a greedy choice and choose the one that is maximum, so as you can see in this slide, the only maximum number is 7, which is greater than 4. So this number 3 will go to number 7, will go to the path of 7. So it will give us a sum of 10. It will give us a sum of 10. And this is a greedy choice. So since we are in the number 7 or the leap 7, so at this moment, we are going to choose which root that we are going to get in. So in this moment, we are going to choose between the 9 and 11. So in a greedy choice, we are going to select the largest number in these two. The largest number. So we all know that the largest number is 11. So 9 is greater than 11. So we are going to choose 11. So from 3 to 7, it will give us a sum of 10. And down to 11, and it will give us a sum of 21. So this is a greedy choice. So in this example, we already achieve or do what is a greedy algorithm all about. So, but uh, we can do better than this. We can do better than this. We can do better than this if we are going to start from number 3 and then we will go to number 4. Then we are going to go choose number 20. Then this path will give us a sum of 27. So this is greater than 1 that we have achieved through greedy methods. So it means that in making a locally optimal method, so it means making a optimal method, the greedy choice is not always uh, give us the a global optimal value. So this is greedy algorithm will never consider our choice. So they will never consider our choice because in the process of doing a minimum spanning tree in doing algorithm greedy algorithm, we always choose what is the maximum number between the two paths. So as we do in my example that we first from root number 3, then we go to path number 7, which is greater than number 4. And next, we choose between 9 and 11. So using a greedy choice, we choose 11 because 11 is greater than 9. So that is the reason why it gives us a sum of 21. But if we are going to do other way, we can do it without using the greedy choice. So from 3 to 4, it will give us 7. So next, we will move to our sample code using a greedy algorithm. So uh, in my example here in the slide is I am using a Python programming language for doing the greedy programming. So as you can see in the monitor that there is a function definition. So the function is we're talking about the definition of greedy underscore coin underscore change, which give us coin target and amount. So the function of a greedy underscore coin and underscore change, it takes two parameter, which is the coin. When we say coin is a list of a coin denominations and the target amount. The target amount is the amount for which we want to make a change. So in sorting that coin, the coin sort is the target, and the coin short is a reverse equals to 2 equals to 2. So the number of the sort coin is descending order. So in this, the line sort the coins list in descending order. This is a crucial step in doing a greedy algorithm, as it ensures that we consider the largest possible coins denominations first. So in change is an initialize as an empty list to store the coins and use to make change. So this remaining underscore amount or equal to target underscore amount is that siya. Change is initialized as an empty list to store the coins used to make change, and remaining amount is the initialize with the target amount. So this grid approach uh, the four coin in coins is a loop iterate through the coin denominations in descending order. The while underscore remaining amount is greater or equals to coins loop continues as long as the remaining amount is greater than or equal to the current coin dominations. Inside the loop, the largest possible coin is added to the change list, and the remaining underscore amount is reduced by the value of the added coins. So this process continue until the remaining amount is less than the current coin denomination. So after the loop, then the function check if the remaining amount is zero. So if it is the function return the change. So is indicating a successful change. If not, it prints a message starting that a greedy algorithm couldn't find a solution in return is none. So in this example, using a selection initialize a list of coin denomination and a target amount, the greedy underscore point underscore change is a function called with this parameter, and the result is stored in the result variables. So the result variables. So if the coin is found, then it prints the result and showing the coins used to make change for a given target amount. So this greedy algorithm works by always choosing the largest possible coins denomination at each steps and reducing the remaining amount until the target amount is reached. So keep in mind that while the greedy algorithm is intuitive, they may not always provide an optimal solution for every problem, just like what next is we are going to discuss Prim's algorithm. So, Prim's algorithm is also a greedy algorithm. These algorithms start with a single node and moves through a several adjacent nodes in order to explore all the connected edge along the way. So these algorithms start with a single in Prim's algorithm. The algorithm start with a single node or any arbitrary node and considered it as a part of the minimum spanning tree. So this greedy approach is At each step, the algorithm greedy select the edge of the smallest weight that connects a vertex in a minimum spanning tree or a vertex outside the tree. This is to ensure that algorithm always chooses the globally optimal solution with the hope that the final solution will globally optimal. So as the algorithm progress, it explores the adjacent nodes and adds the edge with a minimum weight that connects a current minimum and spanning tree to a vertex outside the tree. The process will continue until all the vertices are included in the minimum spanning tree. By choosing the edge with the smallest weight at each step, Prim's algorithm guarantees that the overall weight of the trees is minimized. The algorithm is efficient and has a time of complexity of O, or shall I say E plus V log V, and then where E is a number of the edge and V is a number of the vertices in the graph. So in summary of Prim's algorithm, it is a greedy algorithm that systematically build a minimum spanning tree by iteratively selecting the edge with the smallest spanning tree to a vertex outside the tree. Here is an example of Prim's algorithm or Prim's spanning tree. So considering the following graph is an example which we need to find the minimum spanning tree or the MST. This is an example of a graph. So this is an example of the graph. So next is first we need to select an arbitrary vertex that acts as the starting vertex of the minimum spanning tree. We have here selected vertex 0 as a starting vertex. So as you can see on the monitor, there is a highlight. The number 0 is highlighted. So it means that 0 is selected as a starting vertex. Next is to the edge of the connecting in the incomplete MST. And other vertices are the edge. They're the edges which are the 0 and the 1 in the 1 and the 0 and 7. So between these two, the edge with a minimum weight is 0 and 1. So we include the edge of the vertex is 1 and vertex 1 in the MST. So as you can see in the monitor that 1 is added to the MS3 and this minimum weight edge from MS3 to other vertices is 0 to 1 and then with a weight of 4. So next is the edge connecting in the incomplete MS3 to the other vertices are 0 and 7 and 1 and the 2. 1 and 2. So among this edge, the minimum weight is 8. So this is the minimum 8 is weight. So is 8. So which is one of the edge is 0 is and 7 and 1 and 2. So let us here include the edge of 0 and 7. So and the vertex is 7 and the MSTC. So we would have to include the edge of 1 and 2 with a vertex of 2 and then in the MS3 we include 7. We added 7 in the MS3. So next is edge the connected of the incomplete MS3 with French vertices are 1 and 2. So next 1 and 2 and 7 and 6 and 7 and 8. So there is a 1 and a 2 and there is also 7 and 6 and there is also 7 and 8. So in the vertex 6 in the MSC as at least a minimum the least weight. So the minimum weight edge from the MST in order into other vertices is 7 to 6 with a minimum weight of 1. So in here we are going to uh, add 6 to our MST. So from 0 and 1, and then 0 and 7, and then from 7 to 6 with a weight of 1. So 0 and 1, there is a weight of 8. 0 and 7 rather, there is a weight of 8. And 0 and 1, there is a weight of 4. So next is, we are going to have a connecting edge right now, which is the 7 and 8. So 7 and 8, we also have 1 and 2 again, and 6 and 8. So in our vertex, we are going to include the 5 in the MS3 as our edge has the maximum weight among among them. So in here, we are going to add the vertex 5 from 6 to 5 with a minimum with a weight of 2. So from 6 to 5 with a weight of 2. So next is we are going to include number 2 in our MS3. So from 5 to 2, from 5 to 2, there is a weight of 4. So, ibig sabihin, hindi siya kinonect natin from 1 to 2. So, since this is the edge of our minimum spanning tree in the Prim's algorithm, so this will be the one to connect from the other node, which is it number 2, that have the vertex of 2 and the weight of 4. So next, we are going to connect again between the incomplete chemistry, which is the edge of minimum weight of 2 and 8, the 2 and 8, and then the 2 and 3, or the 5 and 3, or the 5 and 4. So this one, we are going to include in our vertex number 8. So from 2 to 5, and then 8, so 5 to 2, and then 8 2 to 8 with a weight of 2. So next is we are going to add in our expanding tree the number 3, which has the weight of 7. So next is we are going to add the vertex 4 with the weight of 9. So this is our Prim's algorithm in a minimum spanning tree. So this will Our next slide is I also have prepared here a snip code for using a Prim's algorithm. So this code is there, as you can see, there is a head queue. A head queue is a module. A module is imported which provides an implementation on the heap queue algorithm, which is priority or priority queue used in the algorithm. So in the Prim's graph, this prim is function takes a graph represented as an adjacency list where each vertex is associated with a list of neighboring vertices and their corresponding edge weight. So the start vertex, so here is the start underscore vertex is equals to list open and close graph dot key and then 0. This is the choose any starting vertex. So this start vertex is a set to the first vertex in the graph. So this can be any vertex as the choice or the starting vertex does not affect the result. So this visited is equals to open and close start underscore vertex is initialized as a set of continuing the starting vertex. It representing the set of vertices visited so far. So the edge is initialized with the edge connected to the starting vertex, formatted as a tuple or a weight or start underscore vertex or a neighbor. So these edge are added to the priority queue when the and are sorted by their weight. So in the main loop or while edge continue until there are more edge in the priority queue. So inside the loop is the smallest edge includes the weight or the current vertex or the next vertex is popped from the priority queue using a head queue and head pop edge. So adding to the minimum spanning tree, into the minimum spanning tree, the next underscore vertex not in visited. So uh, this set is added to the visited and the edge is added to the minimum spanning tree, which is the MST. So for each neighboring vertex or the neighbor or the next vertex, if the neighbor is not the visited set, or a new edge is created and added to the priority queue. So this process continue until reachable vertex are visited. So the result of this is the function return and the minimum spanning tree, which is list of edge in the order they were added. So an example of the graph is defined as an adjacent list. So the prim function is called with a graph and a resulting minimum spanning tree is stored in the minimum underscore spanning underscore tree. Finally, the minimum spanning tree is printed. So this implementation of Prim's algorithm grows in the minimum spanning tree by iteratively adding the smallest edge and connects the visited vertex to an unvisited vertex using a priority queue to efficiently select so that is how Prim's algorithm process in the programming. So next is the last MS3 category, which is the Kruskal's algorithm. So Kruskal's algorithm is a sort of edge of the given graph in increasing order, then keep it on adding new edges and nodes in the MST. So if the newly added edge does not form a cycle, it picks the minimum weight edge at first and the maximum weighted edge at last. Due Thus, we can say that it makes a locally optimal choice in each steps in order to find an optimal solution. So, uh, the sort edge in increasing order is that initially all the edges of the graph are sorted in ascending order based on their weight. So this is a crucial for the algorithm to start with the minimum weight edge. So the algorithm then iterates through the sorted edge, starting with the smallest weight, and at each step, it consider the next smallest edge and add it to a minimum spanning tree. It doing so that so does not create a cycle. So adding to the edge should not be create closed loop or a cycle in the tree. If adding the edge would result in a cycle, it is skipped and the algorithm move on the next edge. So, ibig sabihin daw, if there is a cycle form in the cross-call minimum spanning tree, it will move to the next edge. It means if that next edge is will create a cycle, then it will move to another edge that will not form any cycle. So to have a local optimal choice, the algorithm makes a selecting the smallest variable. So this algorithm will choose the smallest edge from the other edge. So, pipiliin na talaga yung pinaka-smallest, unlike sa greedy algorithm, pinipili niya kung ano yung maximum number. So, this greedy strategy wherein the algorithm chooses the best option to current steps without considering the overall value of the sequence. So, in the maximum weight edge, the algorithm continues this process until the vertices are connected and the resulting tree spans the entire selection, the entire graph, and the algorithm selection the maximum weight edge among the edge that were considered but not added to the MS3. So, ibig sabihin, if that is a maximum weight, so it will not be added to our Pascal spanning tree, minimum spanning tree. So, this is done by to maximize the total weight of the tree. So, this Pascal algorithm is an example of a greedy algorithm for finding a minimum spanning tree. So, it's worth noting that this approach is locally optimal at each step, but does not necessarily guarantee a global optimal solution. So, nonetheless, for the finding optimal solution, I have here an illustration on how Pascal algorithm works in a minimum spanning tree. So in our illustration, this is the full graph or the main graph. So that is the main graph. So the graph contains a nine vertices. So nine vertices show from start from 0, 1, 2, 3, 4, 5, 6, 7, 8. So it includes the 0. So that is the reason why we have 9 vertices and 14 edges. So when we say 14, we started from 1, 2, and then 3. We are pertaining to the weight of the line which is connected from one edge to another edge. So we have 14 edge. So the minimum spanning tree forward will be having a 9 minus 0 or equals to 8 edges after we are going to sort this spanning tree. So in the illustration from the above approach that the graph contains as 9 vertices and 14 edges. So the minimum spanning tree forward will be having a 9 minus 1 is equals to 8 edge. After sorting, we have the in our example, we have the weight of 1 and then weight of 1, and then we have the source is 7, we have a weight of 1, and then our destination is 6. So that is our first process. So from the source 7, our source is number 7, and we have a weight of 1. And then next is we have our destination, which is 6. So, yan. So that is our first steps in doing a Prim's Pascal algorithm in a minimum spanning tree. So our source is 7. So as you can see in the main graph, so our first source is 7, and then we have a weight of 1, and then our destination is 6. Next is we have a source of 8 from 8, and our destination is 2, and we have a weight of 2. So next is our third process. So from 6, and then our destination is 2. Our destination is 2, and we have a weight of also 2. So next is our source is 0, and our destination is 1, and we have a weight of 4. Next is 2 to 5. Our destination is 5. We start it, source from 2 to 5, and our weight is 4. So, next is, so, ganyan. Same lang siya lahat. Until until we reach the minimum spanning tree for Kruskal algorithm. So that is our minimum spanning tree in Kruskal algorithm. So as you can see, there is a difference between our main graph and to the minimum spanning tree using Kruskal algorithm. So we start it from 7 to 6, and then we start from 8 to 2, and then from 2 to 5. So connect siya. So ibig sabihin, there is no cycle. There is no cycle. Wala siyang cycle na nag-happen. So if this 4 is connected to 1, and 1 is connected to 4, and 4 is connected to 4, 8 is connected to 4, it means there is a cycle. So this will be considered as a graph. So just like in our first slide, so this is the main graph, and this is now our output for the minimum spanning tree in the Kruskal algorithm. So, based in these snip codes that I based in these snip codes that I presented as an example of a Kruskal algorithm. So as you can see, there is a class ununified, and then def underscore inet, and then open and close self, and vertices. So this union find is a data structure. So this is a class of data structure used to keep track of the disjoint set if these two main operation are find and union. So the find is operation is the operations return the representative, which is considered as a root of the set to which of the given elements belong. So it use path compression. It use path compressions to optimize a subsequent find operation. And the union is the operation merge two sets by attaching the roots of the one set to the root of the other set. So it is also used to rank the optimize the union. So in the Kruskal algorithm function, the Kruskal function is takes a graph. So here is the Kruskal function. So it takes a graph represented as an adjacency list and return the minimum spanning tree. So as a list of the edge. So initialize an empty list in the MST to store the edge of the minimum spanning tree. So it create a list of all edges in the graph. So of all edges in the graph, and it sort them in ascending order based on their weight, and initialize a union find data structure. So it iterates through the sorted edge, adding each of the MST. If adding it does not create a cycle, so it means that this set is union find. So the example of the graph is represented as an adjacent list. So in the implementation of the example of this graph is represented adjacent. So the Kruskal function is called with the graph, and the resulting minimum spanning tree is printed. So there is a graph inside that A, and then open and close B and 2 and D 5. Open and close from B A2 and then C1. So this implementation efficiently find a minimum spanning tree of a graph by sorting edge based on their weight and adding it to the MST. So while ensuring that there is no cycle form in the program. So the union find data structure help us quickly checking whether adding an edge that would create a cycle. So that's it for my presentation about the uh, algorithm for MS3 on data structure and algorithm. So thank you so much, and that's all for today.